Here is a question. Read it carefully and think about the answer. Let us solve it step by step. Let us first understand the key concept here. Beta-keto acids, 3-OXO acids, normally undergo facile decarboxylation via a cyclic 6-membered transition state. In this transition state, the beta-carbonyl oxygen acts as an intramolecular base, abstracting the carboxyl of proton simultaneously as CO2 is lost. This requires the molecule to adopt a planar, 6-membered cyclic geometry involving O is equal to CCC is equal to O-OH. Moving on to the next step. The beta-keto acid must be able to form a 6-membered cyclic transition state. This demands that the two carbonyl groups, the keto C is equal to O and the carboxyl C is equal to O, and the intervening carbons can achieve the necessary planar, eclipsed-like cyclic arrangement. Moving on to the next step. In structure, B, the CO2H group and the C is equal to O, ketone, are on adjacent carbons of the bicyclo, 2.2.1, heptane, norbornane, skeleton. Critically, the CO2H is at a bridgehead adjacent position and the ketone is also on the rigid bicyclic framework. Due to Brett's rule considerations and the rigid geometry of the norbornane skeleton, the carboxyl group and the beta-keto group cannot achieve the coplanar, 6-membered cyclic transition state required for decarboxylation. The rigid bicyclic ring system locks the relevant bonds in a geometry that prevents the necessary orbital overlap and ring formation for the concerted cyclic mechanism. And for the final step. Although also on a norbornane framework, the CO2H is on the carbon beta to the carbonyl with sufficient conformational freedom to form the cyclic TS. CPH, CO-CH2, CO2H is a standard beta-keto acid. The phenyl ketone provides the beta-carbonyl, and the 6-membered cyclic TS forms readily. DCH3, CO-CH2, CO2H, acetoacetic acid, is the classic example of a beta-keto acid that decarboxylates easily via the 6-membered cyclic TS. Structure, B, cannot achieve the required cyclic transition state geometry due to the rigid bicyclic framework constraining the spatial relationship between the CO2H and the beta-keto group, preventing decarboxylation. Therefore, the correct answer is B. Therefore, the correct answer is option B.